everyone. In this lesson, we're going to be looking at exponential growth and decay, and I'll be showing you how to write an exponential model to solve real-world problems. And so we have some vocabulary here. The first part here is an exponential function. An exponential function is in the form where we have generally a constant, all right? Could be the value of 1, but it will definitely not be equal to 0. And then we have a base, and then we have our exponent. So this is what we call an exponential function. A growth factor is when we have a value of b that is going to be greater than 1. Exponential growth is a specific way that a quantity will increase over time, and the graph here is an example of exponential growth. So over time, as x gets bigger, y is also getting bigger. You can use an exponential function to model growth if you know the rate of increase, which we call r. And to determine a growth factor, the value of b, we would add r to 1. We can also have a decay factor. A decay factor is a value that's going to be between 0 and 1. So like a half or a quarter or an eighth. Exponential decay is a specific way that a quantity may decrease over time. So if you look at the graph, again, this is exponential decay. Over time, as x is getting larger, y is getting smaller. When an item loses about the same percent of its value each year, you can use an exponential function to model depreciation, the decay in value. To determine a decay factor, we would do 1 minus r instead of 1 plus r like we did with growth. So we're going to look at these. It says determine whether each function represents growth or decay, and all we're going to be looking at is the value of b. If b is greater than 1, we have growth. If b is between 0 and 1, we have decay. So 0.12, that's between 0 and 1, so this is decay. For letter B, 5 is greater than 1, so this one is growth. For letter C, 1/2 is between 0 and 1, so that's decay. And for letter D, 3 is greater than 1, so this one is growth. Does the function y equals 1200, 1.3 to the x represent exponential growth or decay? All right, well, 1.3 is greater than 1, so we know that we have growth. What is the initial value? Now, the value of a in an exponential function represents the initial value. So our initial value in this case is 1200. And then what is the rate of growth or rate of decay? So because we know it's growth, and we know that the rate is the value that you've added to 1. So in this case, we have 1.3. So we've added 0.3. So the rate in this case is 0.3. So we'll say 0.30, or if you wrote it as a percent, 30%. All right, moving on to number 3. It says, does the function represent growth or decay? Well, 0.98 is between 0 and 1, so we know this is a decay function. What's the initial value? The value of a is the initial value. So our initial value in this case is 5. And what is the rate of decay? So the equation that we would set up to help us solve this would be 1 minus r equals 0.98. So if we have decay, we are subtracting the rate from 1. And in this case, we end up with 0.98. So now we just need to solve for r. We solve for r, we get 0.02. So our rate is 0.02, or we could write that as 2%. The annual rate of increase in the U.S. population is about 1.24%. The population in 2000 is 280 million. Write a function which best models U.S. population growth in millions after 2000 and use it to predict the US population in 2015. All right, so we're going to be writing an exponential function, and that would be the form y equals a b to the x. The initial value is the letter a. And we know that we're saying in 2000, our initial value was 280 million. So our value for A in this problem is 280. And we know that we are growing, the population is growing, and it's growing at a rate of 1.24%. So to find B, we would do 1 plus, and we have to convert that percent to a decimal, so that's 0.0124. So 1 plus 0.0124 raised to the value, whatever the time will be in this case. Now, the initial value, the initial year was 2000, and now it's 2015, and we want to predict for 2015, so we're going to replace x with 15. We'll put that in our calculator and see what we get. And if we round that to the nearest million, we get 337 million people. Number 5, Michael bought a car in 2016. The annual rate of depreciation, the decline in an item's value, is 15%. The initial value of the car was $24,000. Write a function to model the situation and determine its value in 2020. So we have depreciation this time. Our rate is 0.15 if we convert that to a decimal. Remember, we're writing our equation in the form y equals ab to the x. Our initial value is a. So we're going to write 24,000 for our initial value. And depreciation, meaning we have a decline in value, so we're going to do 1 minus 0.15. We bought the car in 2016, and now we're talking about 2020, so that's 4 years later. And we're going to put that in our calculator. We get a value of 12,528 rounded to the nearest dollar. That's a true story, by the way. My son Michael bought his car in 2016 and spent that amount of money, so I don't think Michael will be too happy to hear that his car is now worth about $12,000. All right, number 6. I would say for 6 and 7, try them on your own, and when you're ready, come back and watch the video. The first year of a charity event, the attendance was 500 people. It increased by 5%, so we know we have exponential growth. Write an exponential function. How many people will attend the 10th year? Our equation is in the form y equals ab to the x. Our initial value is 500. We have growth, so it's going to be 1 plus our rate, but we have to make sure our rate is in decimal form. And 10 years later, so our value for x is 10. Put that in your calculator. And we get approximately 814 people. Last problem, a piece of land is purchased for $65,000. The value of the land has been decreasing by 1%. Write an exponential function to represent the situation. How much will the land be worth in 20 years, round to the nearest dollar? All right, so we have a decay. I'll write out our function should be in the form y equals ab to the x. Our initial value is 65,000. We're depreciating, we're decreasing in value, so we're going to do 1 minus our rate. And 20 years later, put that in our calculator. And we get a land value of approximately 53,164. Okay, that's all I have for this video. Thanks for watching. Have a great day.